We are in section 7.2, partial derivatives. Remember that dy dx gives the rate of change of y with respect to x. We will now extend this concept to include multivariable functions, functions that are in terms of two or more variables. Partial derivatives of f with respect to x. And you'll notice a little sub x here, and then you'll also notice that there's x's in the denominator because that's what we're taking the derivative with respect to. You will also notice that we don't have normal looking d's there. So that symbol is symbolizing a partial derivative, meaning that there are multiple variables, and we're going to treat x as a variable. And so we're going to be treating x as a variable and y will be treated as a constant. So just think of it as a normal number, not as a variable. And then we also have partial derivatives of f with respect to y. And the difference here you'll note is that we have a little sub y. And you'll also notice that we have y's in our denominator. And that's telling us to take the derivative with respect to y. With this means we're treating y as the variable and x as the constant. So the example right below says let f of xy equal 2x squared y cubed plus 6x to the fifth y to the fourth. Find the partial with respect to x and the partial with respect to y. So starting with the partial with respect to x, and make sure to write that little sub x or some way that we have those different notations to symbolize that you're taking the derivative with respect to x. And so with that, 2 is just a constant and so is y to the third. So you can just go ahead and write 2y to the third. Again, we're treating x as our variable and y as our constant. So then times, and taking the derivative of x squared would be 2x. Plus the next term that we have a 6 and y to the fourth, and those are both just constants, times the derivative, and taking the derivative of x to the fifth, we're going to have 5x to the fourth using our power rule. From here we can simplify this by multiplying things out, and we have 4x y to the third plus 30x to the fourth y to the fourth. From here, you can factor out a GCF, which will help in the next section. In doing so, we notice that we have 2, that's a number, that is the GCF that goes into both 4 and 30, and then also x, and then the smallest exponent that we have is to the third for our y's. And so left over in the first term, we have 2 plus, and then in the second term, we're going to have 15 x to the third y. So we also need to find the partial with respect to y, and this time we're going to treat x as a constant. So this time 2x squared is going to be our constant. So I'm just going to go ahead and write that down, times the derivative of the y variable, that's the one that we're treating as a variable, which is going to be 3y squared plus, and then we have 6x to the fifth, y to the fourth, and that 6x to the fifth would be our constant, times, and then taking the derivative of y to the fourth is going to be 4y to the third. From here we can clean this up, and we have 2 times 3, which is 6x squared y squared, plus, and then 6 times 4 is 24, x to the fifth, y to the third. And then from here we can factor out a GCF, which is going to be 6x squared y squared. First term we only have a 1 left over, plus our second term we're going to have 4. We had 3 x's left over, so x cubed, and we took out 2 of the y's, so just a single y. And that would be our partial derivative with respect to y. The example right below says let f of xy equal e to the 3x squared y. Find the partial with respect to x and the partial with respect to y. So finding that partial with respect to x first. The first thing is that taking the derivative of e to any function is going to start off with e to that same exact function, so e to the 3x squared y, times the derivative of that exponent. And so with this exponent, since we're taking the derivative with respect to x, the 3 and the y are just constants. And then we're going to take the derivative of x squared with respect to x. So that's going to become 2x to the first, or just 2x. We can simplify this a little bit and get 6xy e to the 3x squared y. Likewise, we need to find that partial derivative with respect to y. And it starts off exactly the same way. I'm just going to rewrite our exponential function e to the 3x squared y. Now times the derivative of that exponent. This time the 3x squared is going to be our constant. And then times the derivative of y. And the derivative of y with respect to y would just be 1. And so this works out to being 3x squared e to the 3x squared y. The next example says, let f of xy equal the square root of x to the fourth plus 3xy plus y to the fourth plus 10. Find the partial with respect to x and the partial with respect to y. And so I'm going to go ahead and just rewrite our function first. And instead of a radical, I'm going to rewrite it as a exponent of 1/2. And so we're going to raise this up to the exponent of 1/2. And to find our partial with respect to x, we have to use the chain rule. And so the 1/2 will be multiplied out in front, and our inside function will stay the same. And subtracting 1 from our exponent, we get negative 1/2, then times the derivative of the inside. And remember that we're taking this with respect to x. So the first term we have is x to the fourth for our inside function, which will be 4x to the third, plus, for our next term, the 3 and the y are just our constants, and the derivative of x would just be 1, plus the derivative of y to the fourth with respect to x. Since y's are just a constant, that would just be 0. And likewise, since we have the derivative of 10, that also is a constant, and that would be 0. So we can clean this up a little bit. In the numerator, we're going to have 4x to the third plus 3y all over. There's a 2 in the denominator, and then that x to the fourth plus 3xy plus y to the fourth plus 10 is raised to a negative exponent, so it's moving to the denominator, and it's also a 1/2 power, so that's the same as a radical. So radical x to the fourth plus 3xy plus y to the fourth plus 10. This would be our partial derivative with respect to x. So we need to do the same thing to find the partial with respect to y. And so taking the derivative of our function using the chain rule, we have a 1/2 times the inside function will stay the same, just like what it was for the last one. So raise to the negative 1/2, then times the derivative of the inside. Well, the first term that we have is x to the fourth, and since we're taking the derivative with respect to y, our x's are considered constant, so that would just be 0. For the second term, the 3x will be our constant, so plus 3x times the derivative of y, which is 1, plus y to the fourth, taking the derivative, will be 4y to the third, and taking the derivative of 10 is going to be 0. So again, to clean this up, in the numerator, I have 3x plus 4y to the third all over, and again, a 2, and that function x to the fourth plus 3xy plus y to the fourth plus 10 has a negative exponent, moving it to the denominator and the 1/2, making it a radical. So x to the fourth plus 3xy plus y to the fourth plus 10 would be in the denominator and inside a radical. And this is our partial derivative with respect to y. At the top of the next page, we have second order partial derivative formulas. So I'm going to go ahead and give this a star. And the second order partial derivative formulas that we have are taking the derivative a second time. So taking it a second time, you can take it with respect to x twice, with respect to y twice, with respect to x then y, or with respect to y and then x. So that's why there's 4 different formulas here. So this says let z equal f of xy be a differentiable function. We can then take a second derivative with respect to each of the variables. This will give us 4 second order partial derivatives. So again, we have 4 second order partial derivatives. So definitely something to know. We also start on the inside and work our way out. So that inside function will be the first one that we see listed. It tells us what to take the derivative with first. The example right below says find all second order partial derivatives of f of xy equals negative 6x e to the 2y. And in order to get our second order partial derivatives, we need to take the first partial derivatives. And so we need to find our function with respect to x, the partial derivative with respect to x. And this is going to be negative 6. And x is going to be what we're taking our derivative with respect to. And e to the 2y is also going to be a constant since there's no x's involved in it. And then the derivative of x would be 1. So this is just going to be negative 6e to the 2y. And our partial with respect to y, the negative 6x would remain a constant. And then taking the derivative of e to the 2y is going to start off with e to the 2y times the derivative of that exponent, which is just going to be 2. And so this works out to be negative 12x e to the 2y. So from here, we have first taken the derivative with respect to x. And now I'm going to take it again a second time with respect to x. And so now I'm looking at what I have up above. And I have negative 6e to the 2y, which is just a constant. We have no parts of this have an x. And so the derivative of just a constant would be 0. Likewise, to take the partial with respect to x first, and then take respect to y second, we'll do now. And so you have your function up above, and it's already taken with respect to x. And so now we need to take this with respect to y. And so the negative 6 would stay there. That's just a constant. And then the derivative of e to the 2y with respect to y is going to be e to the 2y times the derivative of the exponent, which is 2, which equals negative 12e to the 2y. For our function, the second order partial derivative with respect to y twice is going to be f of y, we already have up above, and then taking the derivative of this a second time with respect to y. The negative 12x is just a constant and will stay there. The derivative of e to the 2y is going to be e to the 2y times 2. And so this works out to be negative 24x e to the 2y. For the next one, we're going to take the partial with respect to y first, and then our second partial derivative will be with respect to x of x comma y. And so taking the derivative with respect to x, that means that the negative 12 and the e to the 2y would just be constants. And then the derivative of x would just be 1. So this is going to be negative 12e to the 2y. And so we have our partial derivative, second partial derivative with respect to x twice, our partial with respect to x once, y the second time is given. We have our partial with respect to y twice. And then we also have our partial with respect to y and then with respect to x. The example right below says find all f partial derivative with respect to x twice and all partial derivatives with respect to y twice of the function f of x comma y equals the natural log of the absolute value of 5x minus 7y. So in order to do this, we need to find our first derivative with respect to x. And so the derivative of the natural log of 5x minus 7y is going to be 1 over 5x minus 7y times the derivative of that function that we're taking the natural log of. And so the derivative of 5x would be just 5. And then the derivative of the minus 7y would be 0 since there's no x values in there. And this would just simplify to 5 over 5x minus 7y. We also need to find the partial with respect to y. And so in doing this, it's going to be the same idea. So we're going to have 1 over 5x minus 7y, which is taking the derivative of the natural log function, times the derivative of that function, which 5x, derivative of that would be 0, and the derivative of minus 7y would be minus 7. So this simplifies to negative 7 over 5x minus 7y. From here, I need to find the second order partial derivative with respect to x. And so we have our first derivative with respect to x up above. And so in order to take the derivative of this with respect to x again, I'm going to have to use the quotient rule. And so the quotient rule works as the bottom times the derivative of the top, which would just be 0 since 5 is just a constant, minus the top times the derivative of the bottom. And again, we're taking the derivative with respect to x. So the derivative of 5x is 5, and the derivative of minus 7y would just be 0, all over that denominator squared. Cleaning this up, the first term would be 0, and our second term is going to be negative 25 over 5x minus 7y raised to the second power. The next thing that we have to find is our partial with respect to y for a second time. And so our second order partial derivative with respect to y twice. Again, we need to use the quotient rule, and it starts off with the bottom, or the denominator, times the derivative of the numerator, which is just 0, since it's a constant, minus the top, or the numerator, which is negative 7, times the derivative of the bottom with respect to y. So the derivative of 5x would be 0, and the derivative of this negative 7y with respect to y would be negative 7, all divided by the denominator squared. The first term is just going to be 0. The second term is going to simplify. And so to simplify this, we have negative times negative 7 times negative 7, or negative 49, all over our denominator, which is 5x minus 7y squared. And this is our second order partial derivative with respect to y twice. The example at the top of the next page says let f of xy equal 9x squared times y squared minus 4y squared. Find the partial with respect to x. And it says now to evaluate in our values, x is 2 and y is negative 1. So the first thing that we need to do is find our partial with respect to x. And taking the derivative with respect to x, that means that the 9 and the y squared are constants, times the derivative of x squared will be 2x. And then we have minus the derivative of 4y squared with respect to x is just 0. So this is going to simplify to 18xy squared. And so now in order to find the partial with respect to x at the ordered pair 2 comma negative 1, again x is 2, y is negative 1, we're going to substitute those into our derivative with respect to x, so 18x times y squared. And so we have 18 times 2 times negative 1 squared, which works out to be 36. Example right below, I'm going to go ahead and circle, and we'll look at this one together in class. At the bottom of the page, it says chain rule for partial derivatives. So suppose z is a function of x and y, each of which is a function of t. Then z can be regarded as a function of t, and the derivative of z with respect to t will be the partial of z with respect to x times the partial of x with respect to t. And you can think of those partials with respect to x parts reducing out, plus the partial with respect to z over the partial with respect to y times the partial with respect to y over the partial with respect to t. The example at the top of the next page says Adam manages a health store that carries two kinds of vitamin waters, brand A and brand B. Sales figures indicate that if brand A is sold for X dollars and bottle of brand B is sold for Y dollars per bottle, the demand for brand A will be Q of XY equals 300 minus 20x squared plus 30y bottles per month. She estimates that T months from now, the brand A price will be X equals 2 plus 0.05 T dollars per bottle, and the price of brand B will be Y equals 2 plus 0.1 square root T dollars per bottle. At what rate should Adam expect the demand for brand A to be changing with respect to time 4 months from now? Should he expect the demand to be increasing or decreasing at that time? So we need to find dq dt when t is equal to 4. So in order to do this, using that formula that we had on the previous page at the bottom, dq dt, taking the derivative of q with respect to t, would be the partial of q with respect to x times the partial with respect to t plus the partial of q with respect to y times the partial of y with respect to t. And if you look at this, the reason why we're going to use our chain rule function here is because our function that we were given, q, is written in terms of x and y. And then we also have our x's and our y's, which are written in terms of t. So you have a few different ways of doing this, and one is by using this rule. Another one is to substitute in those values for x and y, and then it would be in terms of t, and then taking the derivative of it then. But going ahead and trying out this formula, the derivative of q with respect to x, and q is up above. And for our derivative of q with respect to x, the 300 is 0 because that's just a constant. And then we have negative 40x for the second term. And then the third term is 30y, which would just be 0 also. And then taking the derivative of x with respect to t, and that is just going to be 0.05 plus the partial of q with respect to y is going to be, the 300 is 0 because it's a constant, minus 20x squared, that's also 0 because there's no y's in it, so it's just a constant. And then the derivative of 30y is just going to become 30. And then times the derivative of y with respect to t, and taking the derivative of this with respect to t. And if you need to think about this a little bit differently, this is going to be y equals 2 plus 0.1 t to the 1/2 power. And so taking the derivative, we have 1/2 t to the negative 1/2 power using that power rule. And we're going to evaluate this mess at t equals 4. But what I notice is that I also have x's in here, and I don't know what the x value is. But we can figure out the x value by substituting it into the function that we have up here for x equals 2 plus 0.05 times t, and t would be 4. And to work that out, we get 2.2. So we'll evaluate this also when x is 2.2. So substituting these in, we have negative 40 times 2.2 times 0.05 plus 30 times 1/2 times 4 to the negative 1/2. And substituting this in or working it out piece by piece, we have a value of negative 3.65. And so what this means, so we can say, so in 4 months from now, the monthly demand for brand A will be decreasing at a rate of 3.65 bottles per month.